threading issues, then we will talk about the synchronization today. So what is a thread? Thread is kind of the process. It's a part of the processes, right? So a process has the data structure in the memory, so we can load the program instruction to the memory. That is the process. Then we can execute the instruction by instruction. Sometimes we can separate the part of the, we can share the part of the process. This is a process structure. So what? In case we can run independently or the parallel processing copy of the same task, then we can speed up. We can get the better performance of using such a thread comparing to the creating process. Creating process anyway is an expensive job. So somebody tested how much faster using the thread rather than the creating process is around 30 times faster. So we can use such a thread for parallel processing or the better performance. However, sometimes there are issues to use such a thread. So today we are going to a little bit talk about such issues. Is there any issue to use the thread in our operating system? It can be summarized. It can be summarized as this slide. The first semantics of a fork and EXEC system call. That means how can we create a new process? To create a new process, that process should be copy of a clone of the parent process. So you have suppose that you have a process, you'd like to create a child process. So at the time, you can use the two system call. One is a fork, another one is EXEC. After fork, you can copy, exactly copy of the parent for child process. Then after EXEC, it can be separate. The children process, child process can load its own the instruction code program. Then it can be separate process. What about the thread? So for example, you have the 3 threads in your process. What if when you fork and EXEC? According to the definition of the fork, you need to copy exactly the same thing for this one, including thread. Okay? So there are two options. Whether you can keep such a thread information when you create a child process, or you forget about such a thread. Instead, you can keep the parent process structure information. Okay? So some of the Unix system, some of the operating systems support two types of fork. One is you can copy entirely same thing, including the thread. Another one is only process itself. Okay. However, EXEC is not a big problem. What is a EXEC? EXEC you can load its own programming code and separate the shared part. Shared part is the data part, the instruction part. So even either thread, including thread or without thread, it doesn't matter. You can load new program, okay, then use it. So that is the first issue when you design or implement the thread in your operating system. So Unix system, two versions of such a fork. So when you are doing the Unix programming, you can recognize what's the difference between them. The X is not a big problem, so you can run. You can use as normal as a user. Next issue in the using thread is a signal handling. So as we have discussed several times, current operating system is based on the Intel based operating system. What does it mean, interrupt? So you try to interrupt the processor if you want to get a new, if you want to get a CPU resource. So what does it mean, interrupt? Interrupt is kind of signal in case there is an event. For example, from the CPU is running this processor. This processor needs to read the data I from hard disk drive. At that time, you need to ask the disk controller to get this data. Okay. During that time, this processor will be I/O wait, and there might be context switch. So to utilize this CPU resource for another processor, something like that. Once this disk controller get the return of the data I from the hard disk drive, okay, this controller need to inform. This is an event. Okay, if this event means the getting a data I, then need to inform to the computer operating system, specifically your scheduler. So then your scheduler once operating system get the interrupt signal, that is the signal, okay? Then resume the previous process. What if thread? In case of thread, so it will be more sophisticated. So we need to, so just like the general signal handling in the operating system, when you are using the thread, it's the same thing. In case of the event, so you can inform to that the operating system. Okay, there are two types of such a signal. One is the default signal. Another one is user-defined. Default signal means created by the operating system. On the other hand, the user-defined is from the user. Like the exception handling, like the thread. Okay. So what about the multi-thread? It was longer, the table. So each thread is working for the specific instruction. Okay, sometimes you can process the same instruction, but for the different data. Okay, for parallel processing. So when you send a signal, interrupt signal, it can be sometimes entire process or in your thread. Okay, the thread, each thread can be scheduled, right? So because it's kind of the small process. Even though they share some part of the information with the other thread, the main process is independent. The sequence of instruction. So, for example, there is a read data J. So you can stop, then request. Getting the data J from the hard disk drive, then this controller needs to inform to them. How? Interrupt. At that time, it can be specific thread. Or if the sometimes process stop and the read the data and inform to all the thread at the time, entire the thread or process can receive such a data. So it can be the each and every thread, or you can specify such a certain thread to receive the signal. What about the cancellation? So there are two types of cancellation in the thread. In process, it's called the termination, but in thread, it's called the cancellation. There are two types of the cancellation. One is asynchronous cancellation. Is you inform to the in your operating system or process, inform this process is done. So you need to terminate. Cancel. It's immediately cancel. Another one is a default cancel. Default cancel means it's done, but it's still running. Okay, until the data current process is completed. Okay, so you can just inform to the thread. So why don't you start your job? But this thread will not be terminated right away. Instead, until the current, the process is done, it will be completed. Once the current process is done, that is called the deferred cancellation. Probably when you are doing the Java programming for thread, you can make the runnable thread object, then you can start and you can stop. Sometimes when you stop, even though you stop the thread, there is still running until current process is completed. Okay, that is the deferred cancellation. So target thread will not be completed during the deferred cancellation. Once it is done, it will be completed. So need to check periodically whether this thread is cancelled or not. Also, thread had a local storage. It's called the thread local storage to keep the share of data, which means, what about the local variable of each thread? Where do you keep the local variable in the thread? It's a stack. Each thread has their own stack area. So what does it mean? Once this thread is cancelled, completed, this information will be gone, right? So what if I want to reuse, even though that is a local variable, I want to reuse such a data, right? Sometimes if you run the task, like the summer, but multiple, it's a parallel processing. So you create the multiple, many thread, okay? But I have some common data. This is not the global variable, but it's a local variable. If you use such a common data as a local variable, whenever you terminate this thread, it will be gone. You need to load it again. So to address such a problem, so especially in the thread pool, what is a thread pool? Thread pool to speed up creating even the thread. So you can make a certain pool that has the thread structure in the memory. So you can just, instead of allocate the new memory area for the thread, you can specify the address of this thread 0, thread 1, you can reuse. Then you don't have to recreate the data structure in the memory. So faster. So in case you are using thread pool, you can allocate the specific area for thread local storage. This is a local variable, but it will not be gone. Even though it's terminated, it can be reusable. So this task is done. So then, which means it's a disconnect to this one. Then when you recreate the next thread, you can still see the data in the TLS, thread local storage. That is the difference. If you allocate such a variable as a local variable in the thread area, it will be gone when you terminate your thread. However, if you put the data in the TLS, it's still visible, even though you terminate and recreate the thread. Okay? So TLS is unique for each thread. It's an area in the thread. So especially when you are using the thread pool, this is useful. Okay, also as we have seen the two-level model of thread means there are set of user thread, and another one is the set of kernel thread. When you have such a two-level the thread model, you need to communicate each other. Which kernel thread will be used? Which user thread you use? User thread will be managed by the user level, user mode. On the other hand, the kernel thread will be managed by the kernel operating system scheduler. So you need to inform. I'm ready from the user thread. I'm ready, so please allocate, assign the kernel thread to process this. So that is called the opcode. Okay. Scheduler, when operating system receives such an opcode from user thread, user mode to the kernel mode, so kernel thread recognize there is a request from the user, so I need to allocate the one of kernel thread for the user request. So at that time you can run the scheduling algorithm that we are going to discuss later. So chapter 6. So based on the architecture, the structure of the thread, each and every the operating system has their own thread mechanism. Okay, so for example, Windows thread is from the Windows 98, Windows NT 2000, and so on. So each thread data structure has a thread ID, register information, and so on. Okay. There are three major data structure for the Windows thread. One is the executive thread block, and another one is kernel thread block that can handle kernel thread, and TV is the thread environment block. It's like the PCB in the process control block. Okay, it's only for thread. So such a TV is on the user space, or the other, the executive thread block and kernel thread block is in the kernel space. Linux also definitely has the such a thread. Okay, we have seen the pthread, the POSIX thread specification, and but it's called sometimes task instead of the thread, but it's the same thing. So regarding to the system call, you can create the thread using the clone. Okay, so clone allows the child, the thread to share the address space of the parent process. Just the same, the data structure as the process and thread. Okay. So any question in the thread? So thread is quite simple if you correctly understand the process. So we are going to take the share. We are going to share the some part of the process to speed up, to get the better performance. The next topic is the process synchronization. So I think that probably mentioned several times, if we have unlimited computer resource, we don't have to worry about too much for operating system, because one of the main definition of the operating system is coordinate computer resource, right? Because that means since we have the limited computer resources such as the CPU, such as the memory, and even hard disk drive, so limited resource means sometimes slow and the capacity is low. So we need to think about to maximize the utilization and get the better performance. However, even though we have the unlimited resource, infinite computer resource, still we need such an operating system. In case, for example, how many processes are running in your operating system? So many. It's not just one. From the kernel process, there are a lot of processes. Sometimes there are processes, they are looking for same data. This is a shared information, just like the bulletin board. There is a post-it mark, everybody take a look at this information. What if somebody would like to modify, update? Yeah, you can update, then the other student can take a look at the updated one. What if two students would like to update the same time? There might be a problem. Okay? So we need to address such a competition of the multiple process for the shared data, which is called the race condition. So even operating system, even though operating system has the enough resource, still you need to make some algorithm for operating system. For example, such a way to address the race condition. This is called synchronization. So this is called the process synchronization to allow the multiple process running concurrently. Okay, so today we are in this chapter we are going to take a look at what is a synchronization problem in the process management and how can we address such a problem in terms of algorithm. There are different solutions to address the thing. So idea is so simple. We have multiple processes, but we have the shared data. We need to update or sometimes changes such as shared data. So how can we handle it? Simply, this is the shared data 0. There are two students, student 1, student 2. Student 1 would like to increase the value, +1. Student 2 decrease the value, -1. If you allow only 1 by 1, okay, there will not be no problem. Okay, that's one solution of such a thing. This situation is called race condition. Racing. Two students are racing to get the shared data, bulletin board. Okay, this is called the race condition. So the naive way to address such a problem is we can allow 1 by 1. Student 1 first, then student 2. Then student 2 first, student 1. Then it can be 1 or it can be it can be both of them. It will be 0, right? The +1, -1. -1 +1. Anyway, it will be 0. What if you allow to access the same time the bulletin board, which means student 1 copy this, so it's a 0. And student 2 also copy, it's a 0. So student 1 increase the value, that is 1, then positive. Then followed by student 2. Student 2, what's the value? It's a -1. So update, -1. It will be -1. Vice versa. The student 2 first updated, it's a -1. Then followed by the student 1, it's a +1. So it can be -1, 0, +1. So we need to address such a problem, how to synchronize, okay, along the multiple process for such a shared data. One easiest way to solve such a problem is what? Time? Law. So you can assign the law. Actually, you are going to see the solution, main solution of the operating system. That is a critical section problem. Critical section problem is kind of the lock key. So you have one key to update this bulletin board. So you can share. First, I want to use this key. Then modify. Then you can give to other students. So also, this one can be for the critical section problem because we are going to change the data structure of the process, okay, instead of the key or locking. But anyway, in both concept, it's a kind of the locking mechanism. So we will see how can we handle such a problem. So definitely multiple processes are running concurrently. Concurrently means it's the same time, they can do whatever they want. Okay? Also, this process definitely can be interrupted anytime they are following the Intel-based operating system. Okay? Also, each process can be completed partially, which means process has what? Instruction. Okay? When I'm saying plus 1. So student 1 change the value of the post-it routine word plus 1. Actually, even though I describe such an action with one sentence, there are many actions are involved. For example, copy the bulletin board, okay, plus 1. It's another operation. And put it back, writing the new value. So there are multiple operations. In other words, in terms of the computer, the data structure, it has many instructions. So that means it can be the computer operating system allows such a partial execution. Partial execution means it's a instruction by instruction. Can you divide the one instruction to the multiple operation? No. Instruction is the basic unit. It's a minimum unit to address that. So because of that, we will see later another current approach to handle such a synchronization problem is transaction. What is a transaction?
Send data from one location to other location.
Exchanging.
Transaction means it's kind of the transaction. And that is also kind of transaction. Transaction means it's a set of instruction. Then it's a logical unit. The instruction is a physical unit. Even though you want to allow the multiple, the instruction, you cannot divide one instruction into two because it's a physical operation. However, transaction is a concept. It's a logical definition. It's a set of group of instruction that you define. This group of instruction cannot be divided. Okay? So, for example, this is one transaction. One student updates the post-it and write back. That is one transaction. Then this transaction cannot be divided into two. Such a transaction-based management are used a lot. For example, application, web application, any application in the operating system, also database use such a transaction. Okay, many of the such a application level they define such a transaction until, so for example, user click and then send the data to the server and server process it and your card number is sent to the card company and evaluate, validate and go back and return the data. This is one transaction. How many operations are involved? So many operations. That include the transfer the data and something request. But until you see your card number, your transaction is approved, it is not completed until you see such a message. When you see that message, that means your transaction is completed. That is another way of addressing synchronization problem. We will see later. But here we are going to define we are going to address such a transaction problem differently. So first, what is a race condition? Race condition, you need to have multiple processes. When you have the one process, single process, you don't have to worry about this one. There's no race. Since we have the multiple resources, so there might be race condition. Also, another one is shared data. That data should be shared. If data is not shared, it's only dedicated to this data, there's no racing problem. So you don't have to worry about synchronization. Another one is their data should be updated, changed. If this shared data is a read-only, there's no problem. You can allow any process access this data because it's a read-only. So first, multiple processes, and second is a shared data, and last one is a modified. Okay. So at that time we have the race condition. We need to prevent such a race condition to keep your operating system and are synchronized. Okay. We are going to adapt the producer and consumer problem to explain, to discuss about such a synchronization. So we know the producer is creating the data. So as you can see, there is a buffer size, and you put something data in the buffer. That is a producer. So in this case, the value is increased. So this producer increased the count by 1. On the other hand, the consumer from the buffer, it read the data, then minus 1. So decrease the value minus 1. This is the consumer. So we have the two processes, consumer and producer. Then we can define such a race condition like this. What about the counter plus plus? It's a increase value 1. Increase the value by 1. Okay? Counter minus minus means it's a decrease the value by 1. So if we use the instruction, we can divide such a operation by 3 instructions. First, you need to read the data, counter, then save, store such a counter data into the register. Let's say register number 1. Okay? Then increase the value of the register 1. Then write back to the memory such a register value to the counter. Counter is a variable in your process memory in the memory. Similarly, we can find the counter minus minus using such a register information. So how many operations?
6.
Total 6. 3 from the consumer at the producer, 3 from the consumer. Okay. So depending on the order of instruction operation, the output can be various. We cannot guarantee the output. For example, in case count is equal to 5, so register 1 read is a producer. Okay, it's a 5, right? Register 1 increase the value, so register 1 is a 6. And register 2 read the counter, share the data is a 5, and decrease the value 4. And the write back such a data, so counter is a 6, but it's a override by the consumer. So it's a finally 4. It can be 6. It can be 5. So we cannot guarantee the output of the this one. For details of the such a operation, so this is the memory. Okay, then that is the producer, one process. This is another process. Let's say that this process is running on the CPU 1 and the consumer is running on the CPU 2 or the different core. This is the real assembly course. So if you already took the assembly class or the microprocessor or similar embedded programming, you can easily understand. So first load the data from the memory to register, then increment, then the store, the write back to the memory. For the register 1, this is a register 1. So we have the total 6 instruction. So depending on how to execute such a instruction, the output is not guaranteed. For example, there are 3 cases. Case 1 is we can execute the instruction 1 and another. So one from the producer, then another from the consumer, then producer and consumer, producer and consumer. Okay? So read the counter, then say store such a data to the register 1 in CPU 1, and similarly the consumer read the data, so still 5, and store the value to the register 2, then increment by 1, and decrease the by 1. Okay, right now it's a 6 and 4. Then like that, store such a register value to the shared memory. It's a 6, but it's over replaced by the consumer. Okay. And another case is we can start from the consumer, then the producer, consumer, producer, consumer, producer. So we can get the output finally 6. So the last case is we can execute all the instruction for the producer then consumer, or vice versa. All the instruction for the producer consumer then followed by the producer. This time it will be the 5. Okay. So how can we address such a problem? It's kind of the locking mechanism, but we are not going to manage the separate lock. Okay, so it will be more complicated when you have the many processes. Operating system need to involve. Okay, then you are the next. You cannot take care all of this. Okay, which is not recommended because of the performance issue. Instead, we are going to try to solve this problem by the processes themselves. Okay, so for example, if 2 processes are involved, these 2 processes solve the synchronization problem, whether they assign the lock or not. So to do that, we are going to create the critical section. Critical section means this is a process. In the process structure, it's a special area. Okay, it's really critical, the part of the process. Okay, this critical section, there might be instruction or support of the process, but to enter this critical section, you need to get the permission. Even though this is a part of this process, first to enter this section is kind of long. Okay, when you get the permission means when you have the key, you can enter this critical section. So what kind of code can be critical section? So race condition. Okay, race condition in this case, so this read the shared data and operate, then write back. This one transaction can be the critical section part. So what about the other process? This is the consumer, this is the producer, this is the consumer. Consumer has also critical section. So one, if this consumer wanna access this part, then need to get the permission. Who decide? It should be decided by by themselves. Okay, so we will see how can we handle such a thing. So this is what is a critical section? It's a data structure or process. It's a specific part of the process. Okay. So consider we have the n number of process. Each process has their own critical section. Okay. They can do whatever they want for their data structure, like the local variable, global variable, or some update the data, or writing the data to the accounting information, whatever, except the critical section. So once one process in the critical section, and this time, so which means the producer get the key or permission to access the critical section. No other process can access critical section because it's kind of key. How many keys do you have? Only one key. But this key cannot be given by operating system, professor. So you guys can turn around, or whatever the algorithm, you guys can decide whether I can use the key or who is the next. Okay. If operating system need to involve, it will be more complicated and takes a longer time. So that is the critical section problem. How many process can access the critical section? Only one process. Okay. It's kind of the designing protocol. You need to communicate between the or among the processes. Okay. So a little bit more in detail of the such a critical section problem in terms of the process data structure. This is the entire part. So it's a part of the process structure. So entire part. In the process structure, we define such a critical section. However, to enter the critical section, specific part of your code, you need to get the permission. Where can you get the permission? That is called the entry section. Okay. Also, once you complete such a critical code, race condition, I'm done. Then, if you take the key to your home, nobody can access such a critical section. So you need to announce, release such a permission to others. It's kind of announcement to other students. Then next, you cannot decide. Instead, those who are waiting to enter such a critical section will decide by themselves. If you decide, it's kind of it's the same problem as the professor decide who is the next. So I like her, I like her, I like him, so I can give the key to only these 3 students. If you enter the critical section, but if you decide the next one, always you assign your best friend, right? So those who are waiting in the entry section, up to the entry section, anybody, any process can enter. But for the critical section, only one process. Then once this one is done, during the exit section, you can announce, not decide. Okay? You can announce to the I'm done. So there is a key. Then the other professor, the process who are waiting in the entry section, decide who will be the next one. Operating system does not involve, but operating system provide such a key itself, not the decision key itself. So there are different types of solution for such a boarding. Okay, in other words, lock. Okay, like this in your software, in the programming level, you can do such a thing. In the hardware level, you can do such a thing. Even operating system provide such a key. So we will see such a solution one by one. So this is a general structure of the process who are in the racing condition. Okay? So for example, so we will see the simplest case of the race condition to address the problem of the synchronization. Let's see, it's a process I. Okay? Process I has the critical section. So before we enter the critical section, so we need to get the permission. How can we get the permission? See, so while loop, turn is the kind of key. Okay, turn is the variable. It can be shared by other processes. It's a kind of global variable. If turn is J, okay, which means
Axis.
Can I get the T or not?
Yes.
No. I'm the I. Right? I'm the process I. Okay? Then, if turn T is assigned to the J, which means I do not get the permission yet. Who is
Just
taking the such a key? Process J. Okay? While loop. It's a while loop. Don't be confused with such a code. First, Y is a turn because it's J. Means it's an infinite loop. So let's say we have the two process. So process I and process J. Okay? So process I, there is a common variable turn. Turn equal right now is null. Then Y turn is J, which means I do not have the key, which means waiting for loop, whatever. Okay? Similarly, process J, Y turn is equal to I. If this one is I, it's waiting forever. So first you assign is a J. That means process I need to wait. Okay? However, process J is not I, which means exit for loop. Then enter critical section. You can update shared data. Not turn data. There might be different code, like the example of the first the example that we have seen just before. Then once you have done any process in the critical section, you need to exit. Exit means the turn is what? It's the I. Okay. Then this variable is change it to the I. Then this is not J. Right after turn is change it. This is enter critical section. Then turn. Once it is done, turn is I. J. Okay. This will be loop. So this is the critical section, and this part is called entry section, and this is the remaining section. Okay, so this is the most simplest the way of the synchronization problem algorithm. Okay. However, this is not the perfect. That is just that example show the example of what is the entry section and what is the critical section, what is the exit section, what is the exit section. It's not remainder. This is the exit. And remainder means whatever the code you have, you can process it. Okay, this is a remainder section. It's a remainder section. This is the exit section. Okay, this is just an example. Yes.
Should we change the 10 to equal to I in this example? And that then, yes.
Here, this is a right now. This is a process I, right?
Okay.
So process J, turn, change process J. Currently, default value is a J. Okay. Then J, you can enter this one because it's not I, right? Once you have done, when you exit, when process J exit, change the turn value into I. Then it's not J, which means you can exit the while loop, then enter the critical section.
That means that's code is correct.
Yes, it's correct, but it's not perfect in terms of a synchronization problem. We will see why. This is just one example. I'd like to show the one example of this. What is the synchronization critical section? What is the entry section? What is the exit section? So to show such a data structure, I gave you a simple example. Okay. So this is the requirement of the solution of the critical section problem. To solve the critical section problem, that algorithm should satisfy with the three requirements. These are the three requirements. I think that this slide is the most important slide in this chapter. Okay. First one is a mutual exclusion. I think that you can easily understand. In case of race condition, P1, P2 shared data, how many process are you going to allow to process this? Only one. If you allow the multiple process at the same time,